To chair this session, we have with us Professor Steve Kirkland, Professor and Head, Department of Mathematics, University of Manitoba, Canada. Kindly take over, sir.
So thanks very much. Just like to welcome everybody to this session and to say, of course, good morning to you all. It is 6:30 in the morning here in Winnipeg, Canada, and also in Regina, Saskatchewan, where Shaun Fallat is speaking from, and also in Iowa, where T. Krishna Kumar is speaking from. So Shaun, as already mentioned, is a professor in the Department of Mathematics at the University of Regina. He's also a friend and a collaborator of mine, and he's going to speak to us this morning on almost principal minors of symmetric matrix. Shaun.
It's my pleasure to be here today to talk at this very interesting conference. The title of my talk is on almost principal minors of symmetric matrices, a topic which I'm very interested in. I know that lots of folks know about principal minors and principal submatrices, but my plan is to take it a little bit further to another class of important submatrices. So the outline for my talk is presented here. It is rather long, the outline, but I promise you that I don't have a lot of slides here for each section. So the plan is to introduce the topic to you, provide a little bit of sense of motivation, and then take you through a little bit of the history of how we arrived to this study of almost principal submatrices, and that'll be the last two topics 4 and 5, where I hope I can at least give you some insights into sort of how we're thinking about this project. So beginning with the background, so just to make sure that we understand some of the notation that I'm familiar with and hopefully will be familiar to you folks. So all the matrices in this presentation will be square n by n matrices, and I denote that by m sub n. And alpha and beta will typically denote two subsets from the set of integers 1 to n. Once you have selected two subsets alpha and beta, then this notation here, A bracket alpha comma beta, signifies the submatrix of the matrix A, where you choose rows alpha and you choose columns beta, and then you represent that submatrix as follows. And of course, you preserve the natural order of alpha and beta, not to mix up the orderings of those sets. If alpha and beta happen to be the same or coincide, then what we have is what's called a principal submatrix, so one that respects the main diagonal of the original matrix. And instead of designating it A alpha alpha, I'll simply shorten it to A bracket alpha for brevity's sake. Now, once you have square submatrices, obviously the determinant is an important factor. And so when you take the determinant of a submatrix, and in this case I've signified a principal submatrix, you refer to that as a principal minor. So the term minor refers to a determinant of some square submatrix, and in this case I've designated a principal minor. Of course, everyone understands that the rank is an important quantity associated with a matrix, and here I'll just refer to it as the size of the largest invertible submatrix, since I'm speaking about submatrices in this lecture. Of course, rank is defined in many ways, and this is just one way to define it. Now, when you talk about symmetric matrices, or more generally Hermitian matrices over the complex numbers, an extremely important, basic but a really important fact arises. And as I defined above, the rank is the size of the largest invertible submatrix, but it turns out for symmetric matrices, you actually don't have to choose arbitrary submatrices. You can actually just study the principal ones. And so you simply look at all the principal submatrices. Okay, and there's a lot of them, but you just look at all the principal submatrices and you look for the largest invertible principal submatrix. And that happens to also coincide with the rank. I mean, that's not obvious from the definition, but it turns out to be a fact for symmetric matrices. And it turns out to be, that's kind of an important fact that's led to a lot of, it's a lot of the reasons why there's a lot of interesting properties associated with symmetric or Hermitian matrices. And in my talk today, I will concentrate with real matrices that are symmetric. So this fact will indeed arise. Now, I've become very interested in the world of what's called inverse problems associated with matrix theory. And inverse problems are just, problems where you sort of go in the opposite direction to what you're normally taught, say in an undergraduate course. So in an undergraduate course, in linear algebra, for example, often your professor will say, okay, take this matrix and go ahead and find its eigenvalues, or go ahead and take its determinant, or things like this. And inverse problems ask you to do the opposite. Suppose I hand you a list of eigenvalues. Now I want you to find a matrix that has those eigenvalues. So it's not taking an inverse per se, but it's going in the reverse direction that you're typically taught. And a very important and still unresolved problem is what's referred to as the principal minor assignment problem. So if you've been keeping track, you'll understand that there are 2 to the n possible principal minors in an n by n matrix, right? It's just simply the number of subsets, it's just the power set of 1 to n. Okay, so suppose I hand you a vector of length 2n, and I call that vector u, a vector of numbers. And I ask you, okay, suppose those numbers represent all of the principal minors of a potential matrix, n by n matrix. Could you find that matrix? And that's what the principal minor assignment problem is. I'll hand you all the minors, you feed me back the matrix. And this problem is really hard. And as I said, it's unresolved. There are various, proposed and sort of ideas of solution. And Luke at the University of Auburn says propose what I'll refer to as a set theoretic resolution. It's very interesting, the work he's done. It's not what I want to talk about today. And so I've just listed, no disrespect to Luke, I've just listed some keywords that he uses in order to sort of get after this problem. And it's not surprising that these kinds of, Schur modules and varieties arise, because that's exactly what's happening. An equation proposes surprise that arises. But that's kind of the motivation, I would say. The principal minor assignment problem is motivation for me. So instead of solving the principal minor problem, which I'm not going to do, we looked at some sort of variations of it. And so we defined something called the enhanced principal rank characteristic sequence. And so rather than saying, suppose I hand you all of the values of all the principal minors and you find the matrix, we sort of simplified that problem and looked at a different one. And in this case, it's suppose I hand you a sequence of length n, L1, L2 up to Ln, where the LKs come from this alphabet of size 3, A, S, or N. And A signifies that all, in the kth position, excuse me, A signifies that all principal minors are non-zero. That's all I'm telling you. If I put an S in the kth position, then I'm saying some of the minors are non-zero and some of the minors are 0, right? That you're somewhere in between. And if I put an N in the kth position, I require that all of the k by k principal minors, I require none of the k by k principal minors to be non-zero. So I'm not telling you all the values of those minors. I'm simply telling you whether they're all non-zero, some are non-zero, or none are non-zero. And then the question becomes, if you hand me a sequence, can I find a matrix A that has that particular sequence? That's also an unresolved problem, but we can say lots of interesting facts. And so here's some of these facts. And what we've gotten into is sort of looking at pattern avoidance or forbidden submatrices. So as long as you avoid the field of characteristic 2, then these two words, these words of length 3, are not allowed to occur as a subsequence in contiguous form in the enhanced principal rank sequence of any symmetric matrix. So you're not allowed to see these two subwords in there. So if you're gonna, if you're gonna solve this problem here in this sequence, you're not allowed to put NaN anywhere in that sequence, or NaS and so forth. And in fact, we worked out all of the forbidden 3x3 words here that aren't allowed. That doesn't characterize the sequence that I just talked about, but it gives you some hint, right? So, as mathematicians, now we need to worry about 4-letter words and 5-letter words and so forth, if that was something we were interested in doing. And indeed, we've done some work along those lines, but I just wanted to highlight that there. Now, moving further, so we've talked about principal minors in this principal minor assignment problem, and sort of expanding it by simplifying the conditions to this notion of EPR sequence. So I began to work with a grad student who was hoping to become a postdoc of mine, and he proposed the following. He said, look, what if we extend the notion of EPR sequence to something we refer to as QPR, which I'll define for you. Okay, so this is a bit of a mouthful, but I'll try to go through it with you folks slowly. So you have a submatrix. So now the matrix is designated B, and you have some submatrix B alpha beta. And the Q stands for quasi. So this submatrix is called quasi-principal. Excuse me. If, first of all, the matrix has to be square. So you require the number of rows to be the same as the number of rows to be the same as the number of columns. But I require this condition, that the intersection between alpha and beta has to be, well, obviously it's no more than the size of alpha by obvious subset relations, but it can't be any smaller than alpha minus 1. So what does this technically mean? Well, if equality holds here, then I'm just back to good old principal submatrices. That means alpha has to be the same as beta, and that's something I've talked about previously. However, if equality holds here in this lower inequality, then what does this mean precisely? This means that the index sets alpha and beta differ in exactly one index. Okay? And if you have a submatrix that's square, and the row and column set differ in exactly one position, that's called an almost principal submatrix. And so that relates back to the title of my talk, the almost principal submatrices. So what we're going to study is we're going to study these matrices. So both principal and so-called almost principal. And what we did is we mimicked the previous thing. We're going to talk about this characteristic sequence. This characteristic sequence is a sequence of length n. It has 3 letters ASN, depending on whether all, some, or none of the quasi-principal minors are non-zero. So it's the same idea as before, except you're expanding your list of submatrices. You're including this, what I want to claim is an important notion of almost principal. Okay, so the question becomes, can we get after characterizing this sequence? And I want to remind you, and I know I went through this quickly, but we don't know how to characterize whether a given sequence of AS and Ns is an EPR sequence of a general matrix A. We don't have a resolution for that problem. I mean, we're searching for it. We don't have a general resolution. So the idea is, as mathematicians, you understand, look, how about I expand the constraint list? To expand the constraint list, sometimes that introduces more structure, and then maybe you can get after a characterization. And indeed, we were lucky enough to find a characterization when we expanded our list to include quasi-principal submatrices. And that's the theorem here. So you hand me a sequence of length n consisting of the letters ASN in some fashion. Then that sequence is attainable. That is, it is the QPR sequence of some symmetric matrix as long as the field has characteristic 0. We had some little constraint here that we had to deal with. We can probably get rid of that as long as the field, if it had finite characteristic, if it had non-zero characteristic, the field would have to be infinite. But nonetheless, let's just leave it at this stage. This sequence is realizable as the QPR sequence of a symmetric matrix if and only if the last digit can't be an S. So right here, you cannot have an S in this last position. One of the reasons is because the last position only has one minor, namely the determinant. So you can't have an S in the last position. I would consider that an obvious condition. And then here's the other one, is that you can't see this subsequence of length 2 nor this subsequence of length 2. So as long as you avoid those two subsequences of length 2 and this obvious necessary condition, you can find a symmetric matrix with that QPR sequence. So we were really excited to sort of realize an actual, sort of formal characterization, albeit over the fields with characteristic 0, but it finally sort of did give us a broad feeling. And as I said, if you restrict the characteristic to be non-zero, this theorem is not true in general. And so if the finite field with characteristic 2, you end up with problems. But I think if the field is still infinite, this will hold. But nonetheless, it allows for more interesting research. But we were really excited to realize that we finally had a general characterization over these fields of characteristic 0. So then we asked ourselves, look, did this characterization result actually come from the fact of considering almost principal submatrices? And if so, what if I dropped the reliance on principal and only considered almost principal? Will I still get a theorem? And that led us to the notion of APR. So APR, this is what I just asked ourselves, should we just worry about the presence of almost principal minors? So the A in APR means almost. And again, it's the same, you play the same game as mathematicians. We're creatures of habit, and we just go through this idea to see how far we can push this. So I define what's called the almost principal rank characteristic sequence, the same game as before. You have 3 letters, ASN, and you want to see if such a sequence is realizable. Now, let me point you out to one difference. Notice this sequence only goes to length n-1. That's because there are no n by n almost principal submatrices of an n by n matrix. The only n by n submatrix of an n by n matrix is the whole matrix itself, and that's not almost principal. So you have to kind of stop at size n-1. So that's one little difference in this game. But it's a natural question to ask. Well, okay, I think it's a natural question to ask. I mean, some might argue that it may not be interesting, but I think it is. So because almost principal minors may not be understood by lots of people, I'll give you an example. I avoided examples in the previous settings for lack of time. So here's a symmetric matrix, very simple. And I claim if you look at all the almost principal minors, this is the sequence that pops out. So let's just go through this together just so we understand. In the first position, the 1 by 1 almost principal minors are exactly the entries off the main diagonal. You're not allowed to sit on the diagonal. So here, this 1 by 1 almost principal minor is non-zero, but this one is 0. And so that's why I put an S there, because some are non-zero and some are 0. Now, I'm not going to waste your time going through all the 2 by 2 almost principal ones. You folks have better things to do with your time, but you can check that if you here's a 2 by 2 almost principal submatrix, you can check its determinant is 0. And in fact, they're all 0. And that's why I put an N in that spot. And then in the 3 by 3 case, you just have to do a little bit of work to check that some are non-zero and some are 0. But trust me, you can check that. And when you're bored, you can have fun with that. So we started constructing properties. And here's something I mentioned. If the first position here is an N, that means none of the off-diagonal entries are non-zero, which means your matrix is diagonal. Okay, that's interesting. If in the sequence of a potential APR sequence you see a double N, you see N, then you must have N's ever after. Okay? So once you locate 2 N's in a row, 2 consecutive N's, then you must have N's for that point ever after. And it turns out that the 2-letter word NA cannot occur as a subsequence, which is reminiscent of what happened in the QPR situation from before. And not to waste any more of your time, here is a theorem we came up with. It's not a complete characterization, sadly, because you'll notice that I've reduced the alphabet. I took away the letter A. It turns out that insisting on the letter A does lead to some very interesting constraints that we haven't been able to quite understand. But if you drop the letter A from consideration, we can characterize the possible APR sequences. And just as a matter of notation, this N with a bar over it just means N could be repeated, or it may not exist, just depending how you want. So it's similar to arithmetic. When you put a bar over top, that pattern repeats. That's what I mean there. So that's a partial characterization, I suppose, but please notice I've dropped the letter A from consideration. If you insist on putting the letter A in there, then we only really have a necessary condition. And you'll notice that there's this weird sequence that's allowed. And once you scrap that sequence, then these 2 subwords are not allowed. It's very curious what's happening. Here you see NS sits there, but that's the only sequence that can have NS. Very curious. And then if you're not this guy, then you're not allowed to have NS at all. It's strange. So this condition or this condition, not an AND. And now let me just go to one last topic. I think I'm close to having time come up, but I do want to talk about this other notion of rank. So I began my talk by saying the rank was the size of the largest invertible submatrix, and I said for symmetric matrices that rank can be reinterpreted as the size of the largest invertible principal submatrix. So then myself and my colleague that worked on this problem said, wait a second, what if we actually defined a new notion of rank based on the size of the largest invertible almost principal submatrix? submatrix, because that would help us understand these sequences that I just mentioned a few slides ago. And, because we're not particularly good with names, we just called this the almost principal rank. So you look at all the almost principal submatrices, you take all the determinants, and you find the size of the largest invertible almost principal submatrix. So if I go back to my example that I showed you a moment ago, there is a 3x3 almost principal submatrix here that's invertible, and so the AP rank of this matrix is 3. And it turns out 3 is the largest it could possibly be for this 4x4 case, because the AP rank can never exceed n-1, and because the rank of a matrix checks all submatrices, of course, the AP rank cannot be any larger than the conventional rank. Okay, so there's an example that sort of highlights this. And so we began to study, what could the AP rank be? And we had an idea of what was happening here. We just had to work hard to prove it. And so let me just present to you some facts, and I'll present a simple proof, because I do like to include one proof, but it's very basic because I don't want to waste your time. So the AP rank of a matrix is 0 if and only if the matrix is diagonal. That's something to understand. I mean, generally when we think about rank of a matrix, if the rank of a matrix is 0, then you've got the 0 matrix in your hand, but not for the AP rank, because the AP rank in some regard ignores the diagonal. But if you have a matrix that's, okay, symmetric is the overarching. Now I don't want to be diagonal anymore because I understand diagonal matrices. So suppose I'm non-diagonal, and suppose it happens to be invertible. So I hand you an invertible non-diagonal matrix. What is the possible AP rank? And this wasn't a surprise to us. The AP rank can't be too small. In fact, if the rank of B is n, then the AP rank has to be n-1. And this isn't a surprise. And I suppose if folks thought about it for a little while, you would see that this is, and here's one proof that we came up with. The matrix is invertible, so consider the inverse. Now, because I've assumed the original matrix was not diagonal, it turns out the inverse cannot be diagonal. Because if the inverse of a matrix is diagonal, then the original matrix must have been diagonal, because BB inverse is the identity, and the identity is a diagonal matrix. So if I start non-diagonal, the inverse is non-diagonal. But everybody knows that the entries in the inverse can be calculated using the adjugate matrix divided by the determinant, and the entries in the adjugate matrix off the main diagonal are almost principal minors. You can check that. And so this is a simple little proof that if the rank of B is n, then the AP rank is n-1. So then the natural connection is, look, is the AP rank always 1 less than the rank? Right? So here the rank is n, here the AP rank is n-1. And so we were led to this question, and in fact we say, first of all, the answer to that question is no. The AP rank can equal the rank, and this is a situation where it can, but it is not too far off. So please don't fret about all the notation here. Simply just concentrate on this inequality. As long as you have a matrix that's not diagonal, I mean, the diagonal guys are kind of the 0 matrices in this world. So suppose you have a non-diagonal matrix. That means it's interesting. Then the AP rank is always between the rank and the rank -1. And then the question is, how do you characterize when it's one or the other? That depends on this parameter t that I just mentioned here. But I don't want you to fret too much about it. I just wanted you to be aware of this inequality. And I don't think this is actually a surprise to many people, because the almost principal submatrices are so closely related to the principal submatrices. But nonetheless, we get the result that we desire. And so we are very happy about that. Okay, in the last minute here closing, I have just a couple of comments to say. So the work on the almost principal part and the quasi-principal part was work with this gentleman, Xavier Martinez Rivera. So I appreciate his kind help and work. And of course, the opportunity to speak at this meeting is wonderful. I certainly appreciate it. And I need to thank everyone for their help in assisting me in arranging this presentation. Prasad and Umash Shakara. I know I didn't say that very well. I apologize, but I appreciate all your time and help. Here are some of the references, and I'm happy to take questions if you have any. Thank you very much for your time.
Thank you, Shaun. We have just a brief amount of time. Are there questions for Shaun? I have a question.
It's a question. Not today.
Okay.
So can I make a comment?
Please.
Somebody is trying to come in.
Notion of, I think it is by Fiedler, of the off-diagonal rank. That means you look at all submatrices which do not intersect the diagonal and take the maximum rank. I think it is called off-diagonal rank. And there are some very interesting results about inverse of a tridiagonal matrix and how the off-diagonal rank features. So this is more of a remark that have you looked at the notion of off-diagonal rank, and maybe it will suggest some problems. So just a remark. Otherwise, it was
Thank you for the question. I haven't considered formally the off-diagonal rank. I know what you're meaning concerning the inverse of tridiagonals. Those are called, I believe they're called like Green's matrices. And so there's this idea that somehow off the diagonal in a tridiagonal case, the ranks are 1, I believe. You know, they have this very special property. But I mean, we basically started at principle and we just started to move away from the diagonal in a different sense, where you compared the intersections of rows and columns. But it's a worthwhile, you know, property idea for sure. But I have not formally considered it in terms of these sequences or inverse problems. Thank you.
Thanks very much. Let's thank Shaun virtually one more time.